isn't actually going to be the Interstellar series. I'm going to do a few videos just on some of the concepts in Kerbal Space Program. And not just Kerbal Space Program, but actual real rocket science, space travel. We're going to delve into some of those subjects just so that some of the newer ones can understand some of these concepts a little easier. So, today we're going to concentrate on delta V. Now, that's probably a word you've heard spoken a lot, especially on this channel. And what delta V is, it's actually literally the change in velocity. Now, as we're orbiting, or if we're going through atmosphere, whatever it may be, we have a velocity that we're traveling at. So right now, to orbit Kerbin, we are traveling at 2,246.1 meters per second. So that's the speed that we're traveling at. That's the speed that's necessary to maintain this orbit right here, 100 kilometers. So that's the speed that we're traveling at. Now, if we want to change our orbit in any way, if we want to go higher in our orbit or lower, for instance, if we just want to have a higher orbit, or if we want to, say, go to the moon or go to a planet, no matter what it is we're doing, we're changing velocity. That's what our engines do. So that's what delta V is. It is the change in velocity that we enact through our engines. So different engines have different efficiencies. They have different thrusts. They have different weights, of course. I've actually configured this craft and the other ones that we're going to be dealing with to have as close to 500 meters per second of delta V as possible. So that number right there, 500, it's 516 for this one. 516 meters per second. So that means that we can actually change this velocity to either more, 516 meters per second more, or 516 meters per second less than our current velocity. So we can change our velocity by our potential delta V right here. It all matters how we spend it, but that's how much delta V that we have. So I've had to kind of finicky mess around with this to get it at just the right spot. But let's put some delta V into action. Of course, when we're talking about burning delta V sometimes, or spending delta V, there is no substance called delta V that we're setting fire to change our velocity. It comes in the form of liquid fuel and oxidizer for most engines in the game. So we have 18.24 units of liquid fuel and 22.29 units of oxidizer on board right now, and those together will create that 516 meters per second of delta V for us. So what we'll do is we're going to burn that liquid fuel and that oxidizer together and see what it actually does to our orbit. And of course our velocity. So right now I'm pointed prograde. Let's look at the map. We're right here. We're in a perfectly circular orbit. So what I'm going to do is just activate our engine and go full throttle immediately. So right there we can see our orbit, our orbital velocity is increasing. according to the amount of delta V that we had. Now, as I was just recording this, I actually did just add up our previous orbital velocity and our delta V as provided by the flight engineer, and it came to 2,761. Now, we're slowing down a little bit because it's an elliptical orbit, but we did hit exactly 2,761 meters per second. And we can take a look at the map at what that did to our orbit, and we can see that where it was perfectly circular around the planet, it's now pushed us all the way out here. So that right there is delta V in action. A change in velocity here has resulted in a change in position over here. But notice that it didn't really make too much of a difference to us right here, where we actually performed the burn. That's for another episode, but that's delta V in action right there. We've changed our velocity, and that's had a result on that trajectory. Now, what we'll do, just to demonstrate that delta V isn't just one way, it all depends on how you use it, let's point retrograde and perform that exact same experiment. So right now we're traveling at 2246.1 meters per second, and this time, since we're burning retrograde, we should be looking for a resulting speed, velocity, of 1,730. Yep, I did just make that calculation on the calculator. So, we're pointed in the correct direction, engine is armed, and full speed ahead. So same thing again, we're seeing our velocity reducing as we're burning, and our delta V is coming down, so 1,730 on the dot. So that is the result of burning in a different direction. You can see the difference that has made in our trajectory. Instead of pushing further out, it's pulled us in. We're actually going towards the planet. And that's because we've slowed down. We don't have the kick to get around the planet anymore. So that's with this craft. Now let's take a look at a different craft. Okay, so here we are again. Exact same orbit and exact same orbital velocity, of course. And we also have the same amount of delta V. We have 512 meters per second of delta V. Now, of course, the thing that's different is this craft is much bigger. If you'll recall, the previous one had a little bitty fuel tank, and the engine was about out to here. So this guy is so much bigger and so much bulkier, but it still has the same amount of delta V. So what we can also look at is the amount of oxidizer and liquid fuel that we have. We have 139 oxidizer and 113 liquid fuel. So we have like 5-6 times the amount of fuel, and a much larger engine, but we have the same amount of delta V. So let's see what happens. We know what's going to happen. We have our orbital velocity that's going to add our possible delta V, and that'll kick us out in our orbit. So let's activate our engine and hit the throttle. Now, what did we notice there? We got the same result. We got into the same orbit, kicked out like that. Now, another difference we saw there was how quickly it went. The other one took a good few seconds to burn off all of its fuel. This one took maybe a second or two. And it burned through all of that oxidizer and liquid fuel. It burned through all of our fuel to make that same change in velocity to reach that same orbit as the previous one. So now we're getting into why we use delta V as a measurement for instance, going to the moon, going to Duna, wherever it may be. We use delta V to measure that because it doesn't change. From craft to craft, it's going to take the exact same amount of delta V to get from Kerbin to the moon. Whether it's a tiny little satellite or if it's a huge space station. And we've kind of demonstrated that here through this massive engine and a whole bunch of fuel, and the previous craft, which was just a little bitty thing. Both of them are so different, and yet they took the same amount of delta V. And so that makes it easy for us to say, yeah, you need X amount of delta V to get to the moon. And we can document that, and we know exactly what is going to be required. We don't say, well, you're going to need, let's say, 500 units of fuel to get to the moon if you use this engine, and you're at this mass, and you're at this, and this. It takes all of that out of the equation. It just means, hey, it takes this much delta V to get to the moon. So now we've seen the difference in weights between two vehicles like this. Let's see what happens when we add a payload and see how the delta V changes with that. Okay, so back once again, we're in the same orbit. We have our original Terrier craft that originally had 512 delta V. But now we've added a bit of a payload. And when I say a bit of a payload, it is the science laboratory, and it weighs... actually, it doesn't show how much it weighs right here. But I think it was 2.5 tons, if I recall correctly. So we've added a big ol' payload on this thing, a whole bunch of weight. What's that done to our delta V? Before, it took this to get us to that 512 delta V. Now, we only have 108 delta V to spend. Because we've added this weight, and we haven't changed the amount of fuel, we now can only change this mass by 108 meters per second. And this now gets into what is delta V? How is that calculated? Now obviously we can see right here that the mass of our vehicle has an awful lot to do with it. We've got 1/5 of the delta V that we used to. Now essentially the calculation for delta V takes into account how much thrust we will get from the fuel that we have, how much fuel we have, and how much our craft weighs. So if we have a lot more fuel, then we can go further. If our craft weighs a lot, then we can't go as far. And this is an example of that. So let's go prograde, and we know what's going to happen. We know we've got 108 delta V to spend. We're pointing prograde. We're in our circular orbit. 2246, what's the bet that we're going to hit? Let me do the math real quick. 2,354 meters per second. Let's hit the throttle and find out. Oh. I may need to turn the engine on first. And again, we can see that it's taking about 10 seconds to burn through this. That doesn't change. That doesn't change how long it takes to burn through it. The engine will be operating just the same. And 2,354 meters per second, science. It just works. So let's take a look at what that's done to our orbit. And we can see right there, yeah, we've kicked out a little bit, but not much at all. That's 253 kilometers that we've actually just managed to push out. I don't recall exactly what it was previously on the previous attempts, but that's what we're at now. That's the only thing that we can do with this much delta V. Now, let's repeat our experiment with a different craft again. And yep, we're back with another science lab. So this is just, again, dumb payload, and we've got exactly the same setup as we had with the 500 meters per second delta V earlier. Now, our previous one had 100 and something delta V, the little Terrier. Now we have 350 delta V. So we have about 200 more meters per second of delta V with this setup, even though it's much heavier. So if the weight is a big problem, why didn't this affect the potential delta V of this craft as much as it did the previous one? Well, that's because it's kind of less of a percentage. We've got way more fuel in here to be dealing with this kind of weight. If you have 100 ton, sometimes you can take things to extremes to demonstrate these changes. If we had 100-ton rocket and we added 1 ton to it, if we had a 100-ton rocket that had 500 meters per second delta V, and we added 1 ton to it, it would barely make a difference. But if we had a 1-ton rocket that had 500 meters delta V, and we added 1 ton to that, it would double the weight. It would double the weight, the same mass. So, it doesn't affect all ships the same. The same weight does not affect all ships the same. And again, this goes back to, this is why we use delta V to measure this stuff, so that no matter what we've got on here, no matter if we've just got the engine or we decide to throw on a science lab on our trip to Duna, it's going to cost the same amount of delta V. And all we need to do as we're designing a ship is make sure that we have that requisite amount of delta V. So let's fire this bad boy up and take a look at what it does. Of course, it takes 2 seconds to burn through, and we look at our orbit, and that now has an apoapsis, a highest point of 804 kilometers. So I think that's it for this episode. I just wanted to go over what delta V is. It is the change in velocity. Why it's important, why we use it, which is to say it gives us an easy to use measure that doesn't change from ship to ship of what it takes to perform any specific maneuver to get to a certain place, no matter what our ship it has on board, how it's designed, it takes the same amount of delta V. And also what affects delta V, how we can get the delta V that we need, and that of course is how much the ship weighs, so how much mass we're trying to change the velocity of, how much fuel we have on board. So if we have more fuel, of course we have more delta V. And also the efficiency of our engines, which we didn't really go over today, but we will eventually. The efficiency that our engine burns the fuel at. So if it's a really efficient engine, then it can go further. It can change our velocity more with the same amount of fuel. So that also plays into it. But that'll be another episode. For now, I think that's a pretty decent summary of delta V, and I hope this has been helpful to you in some way. So I will see you again next time.